All right, we may have to turn the light. Is everybody gonna be able to see that okay? A little bright. It's good on the screen, but I don't know if it's good on that screen. That's all right. We're gonna get going. All right, I think everybody's in Pearson now. Did everybody get stuff? I only think we had to send emails back to a couple of folks, but I thought we got that all taken care of. I met yesterday with the MathWorks people. I should have things going fairly quickly on MathWorks, so you guys are probably going to be able to play with MathWorks before the end of the semester. So that'll be really good. But we'll play with Python anyway, so it'll be all right. All right, so we did our introduction into statics on Wednesday. Today, we're going to start dealing with vectors and playing with vectors because we know that our summation of forces, those are vectors, right? And our summation of moments, those are vectors, and we got to deal with vectors. So we will be working with those. Remember that a scalar is just a number. It's going to give, if I look at a scalar quantity, it's going to give me the magnitude or it will give me a value. So we want to look at those. Now, our books and notations, you will see vector notation like that. That is usually giving us our arrows. In some books, it will just be a boldface type. So if you're out there looking at other websites or other things, it'll be a boldface type, but you have this that we're dealing with. Magnitude, remember our magnitude is signified by that. Sometimes it'll use italics for the magnitude. And just to remember that if I have a vector A and I have it in Cartesian coordinate type things, we're going to have our AX in the I plus our AY in the J plus our AZ in the K, where I, J, and K are our unit vectors in their respective dimensions. The magnitude of A is going to be the square root of AX squared plus AB squared plus AZ squared. And for right now, I'm not going to focus today. I'm not going to focus on dot products or cross products yet. We'll get to those later. But remember that if I have a scalar product like a B with my A, that is going to be BAX plus BAY plus BAZ. So you would have that, and we can play with those scalars. So you would have that magnitude. If our value is positive, we're in the positive direction. If I have a value that's negative, it's in the negative direction. So if I do a -1A, it ends up as -A, and that's going to be in the opposite direction of my original vector. Hopefully none of this is new. I've tried to beat on you way back in Engineering Physics 1, and this is the reason. One of the interesting things is that if I take 2 plus 2, that equals 4. If I'm doing two scalars, right? But if I do a 2-pound vector plus a 2-pound vector, that may not necessarily be 4, right? Because that's a magnitude and that's a magnitude, but my magnitude of the ultimate vector may not be that way. And because we have to do our vector addition. So remember my vector additions. So if I have a vector A, here's my vector A. I can write that vector as, so my vector A, we can actually say that that is, we're going to do that as a 1 in the I direction plus a 1 in the J direction. And my vector B, we're going to make it like this. This is going to be vector B, and vector B is 1 in the I direction. A plus B, if I do my vector addition, is going to be 2I plus 1J. If I'm doing it that way, but remember, I can add my vectors. So if I'm drawing in my paper here, I'm going to add my vector A, and I'm adding my vector head to tail. My resultant vector is this one. And of course, we've got our units because I did it on nice paper here. There's my 1 and there's my 2. So my resultant vector is A plus B. And that will end up giving me, if I want to do the magnitude, it's going to be 2 squared plus 1 squared. It's going to equal the square root of 5. And then I have my angle, and just as a reminder, the tangent of the angle is opposite over that. So my angle is going to be the arc tangent of 0.5. And it's Friday, and I can already tell I'm tired. So it's not one I remember off the top of my head. And that's going to be 26.6 degrees. So again, nothing new. But we're actually going to look at a couple things a little differently, because one of the things that we are going to use is the principle of transmissibility. Now, what's going to be interesting about this is the principle of transmissibility. We can use it in a lot of different places, but it doesn't necessarily apply when we're dealing with internal stresses. So as we get later in the semester, the principle of transmissibility may or may not apply depending on the situation that we're in. But as we start, this is going to work just fine. This is going to say, the definition is that the conditions of equilibrium or motion, but we're playing in equilibrium, right? Of a rigid body will remain unchanged if a force acting at a given point is replaced by a force of the same magnitude and direction, but acting at a different point, provided that the two forces have the same line of action. Okay, this is the fun part. There are a lot of times in engineering and in physics and in science that writing out the definition in words is a lot harder than drawing the picture. Okay, so we had our vector A, right? This is our vector A. We had our vector B. There's our vector B. So this is A and this is B. What this is saying is I can move B to up here. I can slide it up so that I can add head to tail. And my answer is going to be the same. All right. The resultant force of those two vectors is going to be the same. So I'm actually moving it. I can move vector A over here. And I kind of want to do that because I want to show you that this is considered a vector parallelogram. Okay.
Go down.
Oh, move it up. Okay, so I get that vector parallelogram, which makes things a lot easier to deal with, right? Because we know my resultant vector is going to be this thing in the middle. Okay, it's going to be that thing in the middle. And also, that parallelogram is going to start helping us out because we can use some shortcuts. Okay, there's some shortcuts that we can get. So we end up with that parallelogram, and this is particularly helpful when we're dealing with forces. So remember way back when we started defining forces, one of the first things that I did when we defined forces is we had a boat. And our boat over here had a force that was going off in this direction. And we have a force that's going off in this direction. And we wanted to find the ultimate direction that the boat went off, right? Okay. Well, this makes it easier. We can go ahead and do my parallelogram here. And we do my parallelogram here. And we know that my boat is ultimately going to go off in that direction. So it makes things a little simpler. It makes things a little simpler. And if we know we have the parallelogram, life becomes a little simpler as well, because remember, one of the things that we said we're going to use quite a bit is this idea. If I have a triangle, and this is side A, and this is side B, and this is side C, and I know these things, this is going to be little c, this will be little b, and that'll be little a, I can use my law of sines. I can use my law of cosines. And I can shortcut my calculations really quick. I can totally shortcut those calculations. One of the things I didn't give you when we did the law of cosines yesterday is if I want to look at the magnitude, in this case, it's going to be the magnitude of B, because these are my 2A vectors. So it's going to be the magnitude of B. B is going to equal the square root of A squared plus C squared minus 2AC cosine of my little c. That's not one that I gave you on Wednesday. It's not one I gave you on Wednesday. But we still have our law of sines, and remember our law of sines are sine over sine of A is equal to B, sine of B is equal to C, sine of C. So I can use rulers, I can use all kinds of different things. I can use my actual vector additions. We can look at a variety of different pieces. So let's go ahead and let's look at our boat here a little bit. And play with our boat. But this time I'm just going to draw the vectors. So I'm going to give our boat. And I did not bring my protractor in here today, but we'll just play with it. So this is going to be a force of 60 kilonewtons. And this is going to be a force of 145 kilonewtons. We're told that this is a 25-degree angle. And we're told that this is a 30-degree angle. And we want to know what is our resultant force. Okay, so a couple things. Let's go ahead and we're gonna do our transmutativity here. And again, I'm not drawing it nice and perfect, but we can do that. Couple of things. So we look at the way I draw my triangles again. We can play with those triangles. We know that this is a 25-degree angle, right? And if that's a 25-degree angle, we can figure out what that angle is. But we also know, right? Oh. So that's 25-degree angle. Again, it's Friday, so I'm not going to do that. So that's a 65-degree angle, which means that that one has to be 65 plus 90 minus 180. This is our 25-degree angle. So guess what? I know this side. I know that side. I know those two angles. I can calculate the magnitude of this one fairly quickly. Or the magnitude of our resultant, whatever our resultant is. So that one, you can calculate the magnitude of that, but that's not my resultant vector. Telling me it's Friday. So let's do it the long way. So my force one is going to be 145 kilonewtons cosine 30 degrees plus 145 sine 30 degrees, except that's not a plus, that's a minus because I'm going downward. My other one is a 2, that's 60 cosine 25 degrees. That one's plus, this is 60 sine 25 degrees. You guys can do the math. I get a resultant vector of 180 in the I minus 47 in the J. My angle is going to end up being 14.7 degrees. My resultant vector is going to end up being 186 kilonewtons. If we do it that way. But we can also use the other ones as well. All right. This angle identity is- Oh, let's just play with a triangle here. This side is going to be 10 kilometers. This side is 15 kilometers. We're told that this is 20 degrees. Okay, I'm told that that one is 20 degrees. We're going to call this A. We're going to call this B. This is side C. And if that's 20 degrees, this is 20 degrees, this is 90 degrees. So this becomes 110 degrees. So now I have two sides and one angle. We can calculate C fairly quickly. C is going to equal, C squared is equal to A squared plus B squared minus 2AB cosine of C. That's 10 squared plus 15 squared minus 2, 10, 15 cosine of 110 degrees. This is 100 plus 225 minus 300 cosine 110, which gives me 325 plus 103, which should give me 428, and that's kilometers squared. So C is going to be 20.7 kilometers. So if I want to find angle A, I get A sine of the angle is equal to C sine of the angle. So I'm looking for the sine of my angle A is going to be A sine of my angle C divided by C. And that's 10 sine 110 divided by 20.7. And that will give me 0.454, which will be 27 degrees. And if I want to know this angle, I'm just going to take my 90 degrees minus my 20 degrees minus my 27 degrees. And that gives me 43 degrees. And that's the angle, that's the question mark. All right, let's see if I can draw this picture. This is where life becomes a lot easier by using these kinds of ideas. I got a box. Okay. I got a box. And I'm gonna put in my little so you can kind of see the other side of my box. All right, we're looking at a triangle that's made up of one side is the diagonal of the top of the box. One side is the diagonal of the side of the box, and one side is the diagonal of the other side of the box. So that's our triangle that we want to get. And we want to find the black triangle. And we're given that this side of the box is 6.5 feet. This side of the box is 3.25 feet. And this side of the box is 4.75 feet. Okay. So I'm going to give myself some points here. This is going to be point A, this is point B, and that's point C. So we're going to work on line AC first. We're going to use our A squared plus B squared is equal to C squared. And I've got my 6.5 squared plus my 4.75 squared is going to equal 64.8 feet squared, which ends up being 8.05 feet. I'm going to do my BC next. That's 4.75 squared plus 3.25 squared gives me 33.125 squared, which gives me 5.76 feet. Now I'm going to do my AB side, 6.5 squared plus 3.25 squared equals 52.8125 squared. And that's 7.27 feet. So now I have my triangle. It may or may not be drawn to scale. But if this is C, and this is A, and this is B, I get this side, AC is 8.05 feet. BC is 5.76 feet. And AB is 7.27 feet. And if I want to solve for this angle, that angle A, I can go at it do my A squared is equal to B squared plus C squared minus 2BC cosine of A. We just have to make sure we know which sides are our A's and our B's. And I've got that. And so I end up with a squared minus b squared minus c squared divided by a negative 2ac is equal to the cosine of a. If I plug in my numbers, cosine of a is going to equal 0.486, and a will ultimately be 60.9 degrees. And then we can use the law of sines to find the other ones. And you'll get that B is equal to 75.3 degrees and C will equal 43.8 degrees. That one's me. That one's typing. Hang on. That one's 6. Okay. Okay. So we're given that as a reference. And we're given that a vector E is such that it is 85 degrees from this reference point. And we're given that a vector Q is 55 degrees from that reference point. P is given, the magnitude of P is 60 newtons. The magnitude of Q is equal to 48 newtons. We want to find the resultant vector. So now you got tools to do it all over the place. But when you're dealing with two vectors like this, it's just as easy to go that P is equal to P cosine of my angle in the I direction plus P sine of my angle in the J direction, and Q and I just got to figure out my angles, but that's easy enough because P is going to be negative 60 cosine 85 degrees plus 25 degrees. Or I can just do it like that because that's going to give me the proper direction. And that ends up being a negative 20.5 in the I plus 56.4 in the J. This is P. And if I do Q, I get Q is going to equal 8.34 in the I plus 47.3 in the J. My resultant vector is just adding those together. I get negative 12.2 in the I, 103.7 in the J, which gives me my magnitude of 104.4 newtons. The tangent of my angle is 103.7 divided by 2.2. My angle ends up being 83. But you got to figure out where that is, right? You got to figure out what that 83 is. But if that's easy enough, if my P is in this direction, my Q is in this direction, this is the 83-degree angle that I figured out. I got time for one more. This is what you get out of the book. They start doing things like little lock bolts and all these other lovely things, and you've got your picture. So as we know, drawing our picture helps, right? Drawing our picture helps. Well, in this case, because that one's a simple one, I've got an 800 Newton force there. I can draw my parallelogram, and we said my 600 Newton one was over here, and we know that that's a 30 degrees, which is really cool because we've got my drawing here that shows that that one is a right angle. So we know what that's going to be. That's going to be 60 degrees. Here's going to be my resultant vector, R. I've got two sides and an angle. If I want to calculate my angles first, I certainly can. Okay, we can calculate B very easily because I can do C over sine of C is equal to B over sine of B. But I got to figure out my B first, or my C first, because I need that side. C squared is equal to A squared plus B squared minus 2AB cosine of 60 degrees. And I get my 600 squared plus my 800 squared minus 2 times my 600, 800. And when I do that, this ends up being 520 newtons squared. C ends up being 721 newtons. Sine of B equals B sine of C divided by C. And that's 600 sine of 60 divided by 721. I end up getting 0.721, which is an interesting result, but B ends up being 46.1 degrees. But they may ask you what that angle is instead. So watch it when you're in Pearson, when it's asking you magnitude and angle. You may have found this angle and you're right. You type that in and Pearson will say wrong. So you want to find that one? Well, that's easy enough because that's 90 degrees. minus my 46.1 degrees, which is going to give me 43.8 degrees. And that may be the answer that they want in Pearson. So watch and double check exactly how they want to do that. Okay. That's where I'm going to stop today. Hopefully none of this was unfamiliar. None of this should have been unfamiliar. It's a good start. Questions?